In this video, we're going to be doing a Unit 5 rotations FRQ. So, two identical spring scales are attached to a cord that is wrapped around a pulley as shown in figure 1. The two pulleys have identical mass MP and radius RP. However, the pulley A is a solid disk, whereas pulley P has most of its mass located at its outer rim. Both pulleys can rotate about their centers with negligible friction in their axles. The pulleys are initially at rest when the two spring scales are pulled with the same constant force Fs, causing both pulleys to rotate. Predict which of the pulleys, if either, will complete one full revolution first. So what we have is that the torque applied to both pulleys is the same. So torque to both pulleys is the same. So we know that torque is equal to FSRP because torque is equal to FR sine of theta, and we have our radius, and we can see that they are being pulled at 90 degrees, and we know a sine of 90 degrees is equal to 1 on the unit circle. 90 degrees, that is a height of 1 because you're at 0, 1. Now, additionally, we have our rotational acceleration relationships, which is torque is equal to I times alpha. Then alpha is equal to torque over I. So then that means that looking at your variables, you see that the pulley with a smaller I is going to have a larger acceleration, aka it accelerates faster because they're inversely related. Accelerates faster. So now let's compare our rotational inertias. So for pulley A, what we have, let's actually do this up here. So for pulley A, we see we have this solid disk. In the solid disk, your mass is evenly distributed among the entire object. So inertia A is equal to 1/2 the mass of the pulley, or mass of the pulley times the radius of the pulley system, so P squared. Now, on the other hand, so this is solid disk. On the other hand, this is going to be a wheel, almost, that is attached by rims, by these rods. So it's a mass, and it's concentrated at the rim. Mass concentrated at the rim. So IB, system B, pulley B, is equal to MPR squared P. So that means that IB is greater than IA. That's because rotational inertia, it measures your resistance to a rotational force. And that's because in this equation, alpha is equal to torque over I. The pulley with a smaller I is going to have a larger angular acceleration. So that means that your alpha A is going to be greater than your alpha B. And because we know that both of the pulleys, they start from rest. So both of them start from rest. The pulley with a larger alpha will reach one revolution sooner. And we can compare their inertias by simply just looking at the equation. I is equal to 1/2 mr squared. So we can see that our inertia is dependent on two things. It's dependent on the mass and of the object, and it's also it's dependent on the mass distribution and also the radius, or the distance from the center of the axis of rotation that your object is at. So we can see that in pulley A, we can see that a majority of the mass, it is equally distributed. So that means you have more mass closer to the center. So you have more mass close to the center. However, for this pulley B, where all your mass is concentrated at the rim, we have more mass at rim. So because your mass is more at the rim, that means your radius is going to be larger here, but here your radius is going to be smaller. So we can see that I is going to be directly related to r squared. So that means if you have a larger radius, your inertia is going to be larger. So that means that if you have more inertia, if you increase your inertia and you have the same torque that is exerted, they both have the same torque that's exerted. So again, let's look at torque is equal to I times alpha. So if I increase my inertia, that means you have to decrease your angular acceleration. And if you decrease your inertia, you're going to have to increase your angular acceleration if you want to get the same torque, because they're both multiplied by each other. So if you increase one, you have to decrease the other, and vice versa. So that's the reason why. So for this answer, you're going to say that pulley A is going to be your answer that will complete one full revolution first. So we can write our explanation out. So now derive an expression at the time TA it takes for pulley A to complete one full revolution. Let IA be the pulley's rotational inertia of the pulley A. So express your answers in terms of Fs, IA, MP, RP using physical constants as appropriate. So for both of these systems, that mass and that radius is going to be the same, and also the Fs. So this is going to be different, and this is going to be different. So first, let's talk about what Fs is. So Fs is the force from the spring scale. And your radius is just Rp. So if we construct our torque equation, that's equal to Fs Rp, because again, sine 90 is equal to 1. And if we use our rotational dynamics, we know that torque is equal to Ia. So inertia here is Ia times alpha. So we can substitute in our torque as well. We just found that torque is equal to this. So you're just going to substitute that in here where you have torque. So that's going to be Fs Rp is equal to I alpha times angular acceleration. So if you just solve for angular acceleration, it's just going to be Fs times Rp divided by Ia. So we also know that we are going to start from rest. So your initial angular velocity is equal to 0 because you started from rest, and then a force was acted on the object that made it move. So it initially didn't have any angular velocity. And we know that your angular displacement for 1 rev, so this is your that's equal to 2 pi. So we know that theta is equal to 1/2 alpha t squared by using the equivalent analog in rotations for the version that was in kinematics, so in translational kinematics. So you're going to have 2 pi is equal to 1/2 FSRP divided by IA times t squared a. So what this means is you just took that 2 pi there, and you also took this FSIA, that alpha right there, which was this. You just subbed in, and now all you have to do is you have to solve for TA. That's what we want to get. So what you're going to do is you're going to first start off by multiplying both sides by 2. So that's going to be 4 pi is equal to FS, because you wanted to cancel out that 1/2. FSRP divided by IA times TA squared. So now after this, what you want to do is you're going to divide by 4 pi. Or no, you can just multiply the reciprocal here, IA or FSRP. This is IA over FSRP. So this is equal to TA squared is equal to 4 pi IA. And this is FS over RP. So then you just take the root of both sides. And TA is equal to the root of 4 pi IA over FSRP. Is your answer to part B consistent with your answer to part A? Yes, it is. And the reason is because in our equation, we can see that TA is going to be directly proportional to IA. And let me just highlight that. Under the root and TA, they're both in the numerator. And you have to also remember to include that root. So that means that a smaller I is going to mean a smaller time to complete one rev. And we know that since pulley A has a smaller rotational inertia than pulley B, it will complete one revolution first, and this is consistent with prediction in part A. So now for part C, a block of mass M is attached to pulley A as shown in figure 2. The block is released from rest. Describe how the net torque exerted on the pulley and the magnitude of the angular momentum of the pulley are changing, if at all, a short time after the block is released. So what we have to do is we have to find the net torque and the angular momentum shortly after this release. So we're looking at post the release for these two. Now let's start off with our net torque. So we know that the torque from the pulley is from the FT in the string. So let's look at our strings here. We have our FBD that can be drawn. So downwards you have the force of gravity, which is mass times gravity, and upwards you have your tension force. And because we can assume that for this situation, we're just going to say that it's equal to mg. So we're going to set our positive y up here and positive x here. And then here, same thing. This is going to be fg is equal to mg. And we have that t is equal to that. So we know that in order for the block to accelerate downward, so let's actually point our directions of acceleration. We're going to have an acceleration that is downward. It's going to be linear acceleration because we're moving in a line going down. So we can write the relationship that summation of forces is equal to mass times acceleration. So we have a positive mg. That's because mg is in the direction of your acceleration. So we're going to declare that this is the actually positive y, because we can make it easier by making the downward our positive direction for acceleration. So you're going to have positive mg and negative t is equal to ma. So what this means is that as the block speeds up, your acceleration is going to stay constant because your force is going to be constant. So because of that, we can see that the tension remains constant too. So we know torque is equal to TR, tension R, because torque is equal to force times R, and we can see, and we already know sine 90 is just 1. So our force is going to be tension here. So we know that T is constant and R is also constant. So that means that torque is going to be equal to something that is constant. So that means your net torque is not going to be changing. Now, what about your angular momentum? So let's talk about our angular momentum. What is an angular momentum? It's L is equal to I omega. So this means that we can look at our pulley and our block. So as our block falls, the pulley is going to move faster. So if you increase omega, that means that L has to increase because I is going to be constant. So that means your angular momentum is going to be increasing. Not changing for this. Accelerates down, causing the pulleys angular momentum to increase. So this is pulley C. As the long cord of negligible mass is wrapped around the third pulley, pulley C, and attached to a spring scale as shown in figure 3, A, long cord. The spring scale is pulled downward so that it exerts a constant force of magnitude Fs on the cord. As the spring scale moves down a significant distance, the vertical portion of the cord moves closer and closer to the center of the pulley. Predict how the net torque exerted on the pulley and the rotational kinetic energy of the pulley will be changing, if at all, as the spring scale moves downward and the vertical portion moves closer to the center of the pulley. So when the spring scale is moving down, this means the cord wraps closer to the center. So what that means is that the radius the radius of your force is gonna decrease. So let's look at our torque formula. So to calculate torque is equal to RF or FR, like that order more. So we know that here F is going to be constant, which is going to be Fs, but we don't have a radius as constant. We have a radius that is going to be decreasing. So we can see that radius is directly proportional to torque, so also torque is going to be decreasing. Therefore, what we have is it's going to be decreasing. Now, what about looking at our rotational kinetic energy? So K rotational is equal to 1/2 I omega squared. So the force from the spring scale, Fs, that's the spring scale, continues to do positive work on the pulley. And also, even though your torque is gonna decrease, the pulley is still accelerated. Therefore, that means your kinetic energy rotational continues to increase. So this is going to be increasing. So we can write a formal answer for this as the chord